Alrighty, so here we have this handout on kinetic energy. You see the picture of the archer there, wearing the fashionable jumpsuit that most archers like to wear. I don't know about that. Yeah. It says, push on an object and you can set it in motion. If an object moves, then by virtue of that motion, it is capable of doing work. So objects in motion are capable of doing work. It has energy in motion or kinetic energy. And this particular handout refers to kinetic energy as KE. I tend to call it EK. Energy, kinetic is the type. So those are synonyms. The kinetic energy of an object depends on the mass of the object as well as its speed. It's equal to half the mass multiplied by the square of the speed. So there you go. They're just going to give you the kinetic energy formula. It's equal to 1/2 mv squared. Now I'm going to derive that for you to sort of show you where that comes from in a little bit. But for the most part, you just need to know kinetic energy is 1/2 mv squared. Now you have to be careful because you might recall from circular motion, centripetal force was mv squared over r, right? So you can see that this could also be written as mv squared over 2, right? And of course, that's not equal to mv squared over r, unless, of course, the r is equal to 2, I suppose, right? So don't confuse those two formulas, is what I'm saying.
Yes.
Okay? Don't confuse the kinetic energy, 1/2 mv squared. When you throw a ball, you do work on it to give it the speed it has when it leaves your hand. The moving ball can then hit something and push against it, doing work on what it hits. The kinetic energy of a moving object is equal to the work required to bring it to that speed from rest, or the work the object can do in being brought to rest. In other words, the net force times the distance, or the work, is equal to the kinetic energy, or we could also say that Fd is equal to 1/2 mv squared. It's important to notice that the speed is squared, so that if the speed of an object is doubled, its kinetic energy is quadrupled. And I'd like you to highlight that, please. If the speed of an object is doubled, its kinetic energy is quadrupled. And why is that? It's because of the mv squared. Because the v is squared. When you double the speed, you quadruple the kinetic energy. This means it takes about 4 times as much work to double the speed of an object, and also then an object moving twice as fast as another takes 4 times as much work to stop. Accident investigators are well aware that an automobile traveling at 100 kilometers an hour has 4 times as much kinetic energy as it would have had traveling at 50. This means that a car traveling at 100 will skid 4 times as far when its brakes are locked as it would if traveling 50. This is because speed is squared for kinetic energy. So every increase in speed is a significant more increase in the distance needed to stop. Kinetic energy underlies other seemingly different forms of energy, such as heat, light, and sound. And at the bottom there, you'll notice they show that a 30-kilometer-hour car might have a 10-meter skid. Double the speed to 60, you're talking a 40-meter skid, 4 times as long. If you quadruple it all the way to 120 kilometers an hour, 160-meter skid. 160 meters is a long way. Think about the track out back, how far 160 meters is. Okay? So, question at the bottom there in the dark box, when the brakes of a motorcycle traveling at 60 kilometers an hour become locked, how much farther will it skid than if the brakes locked at 20? How much of an increase in speed is that, from 20 to 60?
3 times.
That's a 3 times increase. We're going from 20 to 60 kilometers an hour is a 3 times increase in speed. So what's my distance going to increase by?
6 times.
No, 9 times. It's squared, George, not times 2. Squared. So it's going to be 9 times longer. 9 times longer skid. Right? So if you had like a 40-meter skid, 9 times longer than that, you'd be talking 270 meters. It's a long, long, long ways. Okay? So what do you need to get out of that? You need to know what the formula is, and you need to know that it follows the squared rule, not inverse squared. Okay, flip the page over to conservation of energy. Conservation of energy. More important than being able to state what energy is understanding how it behaves or how it transforms. You can understand nearly every process or change that occurs in nature better if you analyze it in terms of a transformation of energy from one form to another. As you draw back the stone in a slingshot, you do work in stretching the rubber band. The rubber band then has potential energy. When released, the stone has kinetic energy equal to this potential energy. It delivers this energy to its target, perhaps a wooden fence post. The slight distance that the post is moved multiplied by the average force of impact doesn't quite match the kinetic energy of the stone. The energy score doesn't balance, but if you investigate further, you'll find that both the stone and the fence post are both a bit warmer. By how much? By the energy difference. Energy changes from one form to another. It transforms without net loss or net gain. Okay, and here's a little example here. They got a little spring-loaded car. You see that it has, you can just barely make it out, 10 joules of potential energy in the spring, but you only get 8 joules of kinetic energy. What happens to the other 2? Generated as heat. Okay. One of the things that you might find, I don't know if you've ever played tennis or racquetball or squash or any of those kind of games, particularly squash, if you hit the ball lock after a game, if you feel the ball, you should feel that it's warmer. All that whacking it, you're actually converting it to heat. It does heat up. In fact, the ball gets loose, you can actually feel the difference. The study of the various forms of energy and the transformations from one form into another has led to one of the greatest generalizations of physics, known as the law of conservation of energy, which you guys probably all know. Energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes. And when you consider any system in its entirety, whether it be as simple as a swinging pendulum or as complex as an exploding galaxy, there is one quantity that does not change: energy. It may change form, or it may simply be transferred from one place to another, but the total energy score must stay the same. Okay, and you can see that little pendulum there. And we talk more about this when we get into potential energy, but you can see you got it like this, you got it like that, and you got it at the bottom, right? I'm not sure why I drew that line at the bottom. Right? Up here, it's all potential energy. It's at its peak. Here you've got potential energy plus kinetic energy. Not only is it moving, but it's also still raised up a little bit. I didn't draw it very well. And then at the bottom here, it's all kinetic energy. And then, of course, it's going to go back to the top. Now, we all know that if you let something swing back and forth, eventually it's going to do what? It's going to stop. How come? I thought energy was conserved. What happens? Air resistance. Okay. Slight bit of air resistance is actually enough to slow it down. Where does that energy go? Classic answer: heat. Right? We all know what happens to the space shuttle when it enters the atmosphere, right? There's a lot of air resistance. So we're just talking about a small amount. That's all. A small amount of energy. Okay, flip the page over. You should see a little cartoon on the left-hand side there with some firemen catching someone jumping out of a burning building. Perhaps the potential energy has been turned into heat energy, unfortunately, in the form of fire. This energy score takes into account the fact that the atoms that make up matter are themselves concentrated bundles of energy. When the nuclei or cores of atoms rearrange themselves, enormous amounts of energy can be released. The sun shines because some of this energy is transformed into radiant energy. In nuclear reactors, much of this energy is transformed into heat. Powerful gravitational forces in the deep, hot interior of the sun crush the cores of hydrogen atoms together to form helium atoms. And I showed you that video there the other day about the energy of the sun, right? This welding together of atomic cores is called thermonuclear fusion. This process releases radiant energy, some of which reaches the Earth. Part of this energy falls on plants, and part of this later becomes coal. Another part supports life in the food chain that begins with plants. Part of this energy later becomes oil. Part of the energy from the sun goes into the evaporation of water from the ocean, and part of this returns to the Earth as rain that may be trapped behind a dam. By virtue of its position, the water in the dam has energy and may be used to power a generating plant below, where it will be transformed to electric energy. The energy travels through wires to homes where it's used for lighting, heating, cooking, and operating electric toothbrushes. Yeah. How nice that energy is transformed from one form to another. There's your warm fuzzy for the day. What a great thing, this conservation of energy thing. Okay, so if you look there at the cartoon, you got this poor lady who's jumping out of the burning building, and you see at the top she's got 10,000 joules of potential energy. And as she falls, what happens to her potential energy? It goes down. A little ways down, she's got 7,500 joules of potential energy, which means she has to have 2,500 joules of kinetic energy. And as she falls and falls and falls, the potential energy goes down, but the kinetic energy goes up. But the total energy must always be 10,000 joules. Now, is that entirely true? Is she going to have exactly 10,000 joules of kinetic energy at the bottom? No, because she is going to lose some energy due to heat. Okay? And that is exactly how I figured out. And if those of you have ever been to Canada's Wonderland, anyone?
Yes.
Have you?
Yeah.
Awesome. Did they have that big swingy thing? It's like a big, they had like these two towers like this.
Yeah, ball.
And then they had like these wires between them, right? Hanging down, like a big giant swing kind of thing. And then they strap you in right here, right? They strap you in, not by your head. They don't strap you in by your head, thankfully. Right? They strap you in, sort of like that. But they actually put you so you're flying, right? And then they sort of drag you backwards. There's another tower sort of here in the background, kind of thing, with another wire attached to it like this, and then just sort of pull you back, just like a dad might pull a kid up on a swing, you know. And then they give you the ripcord kind of thing, and then you go flying down. So, did you see that? I didn't do it either. I'm a scaredy cat. No? Well, I remember because my kid asked, I wonder how fast they're going at the bottom. Remember I told you the story? And so I used, maybe it was me. I wanted to know how fast they'd be going at the bottom. And so I figured I estimated how high up in the air they were. I used my knowledge of potential energy because it's mass times gravity times height. No, but I just,
How fast do you think you'll be going at the end of this?
I can't help myself. I figured out the potential energy, converted it to kinetic energy at the bottom, and it used 1/2 mv squared, estimated the people's mass, determined their speed at the bottom, and I was pretty right, because when I got home, I checked it out on the internet, and it said, reach speeds of, and I'm like, yeah, that's the number I came up with.
Yeah, you should figure that out. You need to just go on a couple of rides.
Just relax.
Just relax.
I went on the Scooby-Doo coaster.
I did too, and it was terrifying when I was young.
Yes, it was rickety and old, and I was like, well, I'm going to die on the Scooby-Doo coaster.
And then they take a picture of you, and I remember when, that was back when, like, I was little when I went, most of us really, really long hair. They took a picture of you right as you went down
Yeah.
a big, like, drop, and Sarah was like, right up, and he was just screaming, so I was just crying.
Cool. The day we went 2 days, and my son really, really, really wanted to go on the coaster. Okay, so we go stand in line. We're standing in line for like 20, 25 minutes or so, and we're right at these people are going in. I'm like, okay, we're going to be on this one, and they, no, you guys go on the next one. Okay, so we'll wait another 5 more minutes. They start it up, and it's going up the hill, and then you hear this big noise, and then it's stuck there, right? And so I'm like, man, am I ever glad I'm not on that one. So they spent like 10 minutes trying to get it unstuck. These poor people are like stuck on the coaster, you know, going up. They eventually had to like evacuate them. They had to get out and walk down the hill. There were some sort of steps. I'm like, man, am I ever glad that they actually shut it down for the rest of the day. So I spent about 45 minutes waiting, never got on it.
Take your kids in the one where you get into the car, and they give you the gun, and the Scooby was like,
Yeah, that one we spent like about 2 hours in line for that one.
so much fun.
Yeah, it was
You
like,
just gotta, like, shoot.
was it worth it? No. 2 hours we stood in that line. Crazy. All right. So the question is, suppose a car with a miracle engine is able to convert 100% of the energy released when gas is converted, which is about 40 million joules per liter. Okay, so you go buy a liter of gas, you're buying about 40 million joules of energy to mechanical energy. In other words, all of the energy is converted to mechanical energy. There is no energy lost due to heat, which we know isn't true. If the air drag and overall frictional force on the car traveling at highway speed is 2,000 newtons, what is the upper limit in distance per liter that the car could cover at a highway speed? Okay. In other words, how far can you go on 40 million joules of energy if friction force is 2,000 newtons? Does this seem like an easy question to you, or does this seem like I don't know how to do that? So what's going to happen to the 40 million joules of energy? It's going to be used for work, right? Work equals force times distance. All of my 40 million joules is going to go into overcoming air resistance. And so what's my distance? 40 million divided by 2,000. Cancel out a set of zeros. 40,000 divided by 2. 20,000 meters, or 20 kilometers on 1 liter of gas. That is the absolute maximum distance that you can go on a liter of gas.
Because some trucks,
Now, pardon me?
because some goes, I don't know.
Well, because all of the force goes into overcoming, like once you're up to speed, all that force goes into overcoming air resistance, right? That's assuming that 2,000 newtons is sort of an accurate figure, and I believe that it is. So is that good? Like, is that good gas mileage? 20 kilometers per liter? Like, most people figure out their gas mileage in
30
miles per gallon, right? But the metric way to do it is to find out how many. The metric way to do it is liters per 100 kilometers. So, and you actually want the number to be low or high, Jordan, when you're doing liters per 100 kilometers. You want it low. You want a small amount of liters per 100. Okay? So 20 kilometers per liter is equivalent to what? 5 liters per 100. I had a vehicle once that got about 8 liters per 100 on the highway, and that was pretty good for that size vehicle. It was a van.
What's smart?
Yeah, a smart car would not get more than, I don't know what the smart car would get. Someone can Google it up for me, I guess, if you want. But that obviously the 2,000 newtons depends on the shape of the car, right? Right? Like a really aerodynamic car is going to need less. If you're driving a bus, you're going to be very unaerodynamic. So that's about the upper limit, is about 5 liters per 100.